We've seen that we can take the Laplace transform of piecewise functions, but we'd like to be able to do it in a more straightforward or consistent manner without having to resort to the actual definition integral if we can avoid it. Coming to our rescue is going to be a new function called the Heaviside step function or the unit step function. Heaviside is the name of a mathematician / physicist if you're interested. The function is brilliantly simple. The function has a value of 0 up to t equals 0. So on this axis, we would have a flat line. Here we go. And then it would be undefined at that point there. And then it would jump to height 1 for every value of t that's larger than 0. And with little imagination, you can see how that could be used for piecewise functions because it's basically an on-off switch. If we multiply by u, the function stays off until time 0, and then we multiply by 1, and that'll just leave whatever it's multiplied by on for the rest of time. Now that wouldn't be immediately helpful for the kinds of functions we saw before, but with a quick twist, it turns out to be easy to adapt this to piecewise functions that have different breakpoints. Reminding ourselves of the general u function, or the simple one. What happens if we put a -5 in here? Well, back from your knowledge of about grade 9, grade 8 math, this will shift the graph right by 5. And that means that our function will look exactly the same as it did before, except the jump will happen at t equals 5. Filled in circle, and so on. And so as we're going to see, it's going to be straightforward to build functions that are piecewise out of this building block and whatever happens on a given interval. We're going to see a lot of this u of t minus something, though, if the turning on happens at some point that's not time 0. As always, examples are the easiest way to get familiar with this kind of new idea. Knowing that u of t minus a, so some shift that we don't know, is going to be a building block, how will we take the transform of that with Laplace? Well, to take the Laplace transform of anything, we will use the definition one last time here. The definition will tell us that the integral from 0 to infinity of e to the minus st, u of t minus a dt would be the Laplace transform we're looking for. And going back to what we saw when we first did our piecewise functions and their transforms, we would note that u is equal to 0 for t less than a. And what does that mean? Well, it means we can ignore it in the integral. We're going to be multiplying by 0 when t is less than a, so that means we can start our integral at a and go out to infinity. Again, if we think of integrals and we think of what this u function's doing here, there's no sense including the area under the graph for this interval here because it's already 0. We still have the e to the minus st. Now what do we put in for our u? Well, if we're talking about this region here, we're talking about t always larger than a. Well, if t is larger than a, then our function now is just 1 on that interval. So by changing the interval, we can replace the u part with its simpler version 1 because we know we're only concerned with t larger than a. When t is less than a, we get no contribution to the integral. We could throw that away. Well, this is very straightforward. This is just our regular exponential integral. So we're going to have e to the minus st over minus s between a and infinity, and again playing fast and loose with our improper integrals. If we evaluate this as our time value goes towards infinity, we're going to get a 0 minus e to the minus s times a, again recalling that these are t values, and all that divided by negative s, and that's going to give us 1 over s e to the minus a s. All right, this is an important milestone because if you think of the function that we're basically dealing with, it was the function 1. What's the Laplace transform of the function 1? It's 1 over s. And so this part here is what is coming from or capturing the step function, the fact that that function didn't turn on until some later time. So anytime we have a step function and we transform it using Laplace, we're going to end up with one of these exponentials with s's in them. So it can be a bit confusing. We saw other theorems or other table entries that had exponentials in the time domain. Now they're in the s domain. If you keep your table handy as you go through these, you'll find it does make sense. It'll just take a little bit of practice. Speaking of the table, there are two entries that are going to be of particular help to us here. One is going to be the most helpful in the forward transform. This is the one you'll see in most tables, but quite frankly, it can be easily massaged into this form here with a little transformation of functions. And this one you'll find easier to use when you're going forward. Now, just as a notation, sometimes u of t minus a is written as u sub a of t. It's the same thing. You'll see both of them in various textbooks. But the idea is if we have our step function times something else, then we get the Laplace of the original function with a shift of plus a and this negative exponential popping out. Let's see this in practice. If we want to take the Laplace transform of u2, not the band, just the function, you'll have u2 is effectively times 1. And so if we want to recreate that, we would get e to the minus as, e to the minus our a is 2 here, e to the minus 2s. And then we'd follow up with Laplace transform of our function with all the t's replaced by t plus a in this case here. Well, in this function, we just have the 1. So there are no t's to replace. So it's actually pretty simple. And in fact, we get what we saw before, which was e to the minus 2s times 1 over s. So if we have the transform of a constant, we get that transform by itself. The fact that it only starts at time 2, we capture with this exponential e to the negative 2s. Likewise, if we were asked to transform u sub pi, which means the function that turns on, the step function that turns on at time pi, or 3.14 seconds, we would get e to the minus pi s times the Laplace transform of what it's multiplied by, which is just 1. And so we have e to the minus pi s times 1 over s. So those are fairly simple. Let's take a look at one that actually has a time value in it. Here we have the transform of t times u3. Just as a quick sense of what that graph would look like. Remember that u is equal to 0 up to time 3. So we would have a flat line for a while up to exactly time 3. And then after that, we would be multiplying t by 1. So it's like we'd have the graph of t going on, but not turned on yet. And then as soon as we hit time 3, we continue the function already in progress, if you like, of y equals t. So this function here, the graph of it would be flat at 0, and then jump, and then go on like the function t after time 3. What does that do for our Laplace transform? Well, if we have, let's put it in exactly the same order the function here is, ua times a function, now our function is t. What this rule says is, first of all, before you do anything else, you're going to get an exponential e to the minus 3s. And then you're going to follow up with a transform. And here, we're replacing the t's by t plus 3. So we'll have the transform of t plus 3 itself. And this, you'll notice, has no step function in it anymore. So the step function gives us two pieces. One is the exponential with the s, and the other is the shift. Once we've done that, though, we just keep going, e to the negative 3s, and we take the transform of t plus 3. Each of those is in the table as an individual element, and because it's linear, we can do each one separately. The transform of t is the t to the power 1 transform is 1 factorial over s to the 1 plus 1, and the transform of 3 is just 3 over s, 3 times the transform of 1. And so if we're asked to transform this stepwise function here that was 0, then jumps up to equal t, this is the function we're going to get on the transform side. Again, notice the ingredients, transform of t and transform of a constant, and we're also going to have this exponential with an s in it that indicates a step function is present.